Welcome back. This is Charlie's Engineering Corner, and I'm Charlie. This is a four-part series, and its purpose is to teach basic skills on a tutorial basis to maintenance technicians. The first module, which if you haven't checked out yet, you ought to go back and look at it. It's the introduction to electricity. The second module is entitled Electromagnetism. We're going to talk about magnets. We're going to talk about relays and solenoids. We're going to take a look at the symbols that we use to describe the relay itself. Okay, you probably recognize this. It's a bar magnet, and interesting characteristic of a bar magnet is it attracts steel, or specifically iron. It's the iron inside the steel that's being attracted to the magnet. So things like paper clips, steel screws, we can pick up with a magnet. Things we can't pick up with a magnet are pieces of wood, styrofoam, and plastic. Obviously, those don't have any iron in them. And this is why you use the magnet on your refrigerator, because the refrigerator outside is basically a steel sheet, and the magnet holds the paper against the refrigerator. All right, the bar magnet has two poles, one labeled N for north and the other one S for south. These names came from the fact that the Earth has a huge magnetic field going around it, and it stretches all the way from the South Pole up to the North Pole. The Earth's center is made of iron, and the spinning of the Earth and the fact that there's an iron core causes a magnetic field to run around it. So anyways, I liken the bar magnet to the Earth's magnetic field, and that's why it's labeled north and south. If you've ever played with magnets before, you probably already know this, that dissimilar poles, like a north and a south, or the south over here and the north here, attract each other. Whereas if they're the same pole, two norths or two souths repel each other. So let's take a closer look to see why this might happen. Okay, around the magnet itself are these lines. They're invisible, and they're called magnetic lines of flux. And they create a magnetic force field here. These line of flux start at the North Pole and they go over to the South Pole. They're very, very concentrated at both poles, at both the North and the South, but they are spread out in between. So they come out in a radial pattern, and they're not concentrated in the middle of the magnet, but they are concentrated on either end. Let's see if we can't prove this concept. So if you were a Boy Scout or Girl Scout, at some point you took a compass and you read a map with your compass. So you know the compass needle always points to the north, and that would be the red end of the compass needle. The white end always points towards the south. So if I take my compass here and I bring it right on the end of the South Pole, the white will point right at it. As I start to approach the North Pole, then the red needle starts to point directly right at the North Pole. So let's take this compass and move it around at various spots and see what it looks like here. So we took this photo after we had the compass in, I'm not sure how many positions we had, but the idea is to show you that the compass will follow these magnetic lines of force. So Over here in the South Pole, you see right at the end of the magnet, it's pointing directly into the South Pole. Part ways down, it starts to look like 45 degrees. Right in the middle, it's 180 degrees. Now, as we approach the North Pole, then the red needle starts to point towards the north. Over here on the left-hand side, and the red needle is pointing directly into the North Pole, and it continues around on the top of the magnet and get the same results. So the compass is showing us where these lines of force are. Another way to see this would be to take a sheet of paper, put your bar magnet underneath the sheet of paper, and sprinkle iron filings on top. And the pattern that the iron filings will look like is what's shown in this photograph. So you can see that these iron filings get crowded at the two poles. In other words, it's very, very dark here. That's because the lines of flux are very, very concentrated. In the middle of the magnet, they're spread out, but you see this radial pattern again. Lines are going from the North Pole, radiating out, and then coming back into the South Pole, and then it gets concentrated again at the South Pole. So this is another way to prove that these invisible lines of force are surrounding this magnet. All right, let's run another experiment. Let's take a battery, like a lantern battery, and a piece of wire, and connect it to both the terminals on the battery, the plus and minus. Now after you connect that, take a compass and hold it near the wire. Run the compass around the wire. You should see the needle pointing directly right at the wire. If you shut off the current in the wire, then you'll see the needle and the compass point to the Earth's magnetic north and south. Then you might want to try reattaching again. You'll see it snap right back to the wire. So what does that mean? It means that the magnetic field around this wire, just like we had before on our bar magnet. If you're actually going to run this experiment, keep in mind that, as we talked about before, that short piece of copper wire doesn't have very much resistance, right? We talked about that earlier. If it doesn't have much resistance, you're going to get a lot of current through the wire. What happens with a lot of current running through the wire? Well, the insulation is going to get hot, and you may actually smoke it. So we're going to go one step further now. We're going to go get real thin copper wire. It's called magnetic wire, and you'll see why in a minute, why it's called magnetic wire. We're going to wrap it around a steel bolt. And again, remember, steel has iron in it. So we wrap it around, make a lot of coils, maybe 25 to 50 coils. And then we attach the clip leads from our battery back to this wire. And lo and behold, put it near some paper clips down here, and the paper clips are picked up by it. It's just like the magnet, the bar magnet we had before, right? Well, this is called an electromagnet. It is, in fact, a magnet. One end is north, one end is south. If you took that compass, you could figure out which end is north and which end is south. All right, let's take that same concept one step further. Let's wrap the magnetic wire around the bobbin. The bobbin has a hole in the middle, right? Now let's take a steel bolt or a steel rod. Let's use a steel rod and place it in the center where the hollow part is. When we connect our wire to the battery this time, you'll see that rod gets sucked in or being attracted by the bobbin. When we shut off the current to the wire, then we can move the steel rod anywhere we want and it stays put. But as soon as we connect it back up, then it's pulled back into the bobbin. So we've got another electromagnet, and we're pulling on this external rod. This is basically how a solenoid for either pneumatics or hydraulic, a solenoid valve works. There's a coil, and inside the coil is a poppet. The poppet is made of steel. You're pulling the poppet out of the seat, and that causes a pressure difference across the seat, and that is used to shift a spool valve. It's also used in relays. The bobbin itself is a coil, and we're going to pull on an armature. We're going to call it an armature. The internal piece we're going to call an armature. All right, so from the previous slide, this is a lot like our bobbin, right? We've wrapped all these coils of wire around this piece. In this case, our armature is not moving, the center is not moving, but we have a steel piece on the outside. It looks like a lever. It'll pivot at this point right here. It'll pivot up and down, and it's actually spring-loaded up. When we take our bobbin or our coil and we energize it, and the magnetic field pulls this lever down. Now, on the end of the lever are two copper contacts. If I don't turn the current on, the contact is up all the time, and that side we're going to call normally closed, because when I walk up to it, there's continuity between this end of the lever and the top, and the contact is closed by itself. When I go and operate the battery, then the magnetic field pulls it down, and now the circuit is from the end to the bottom contact. This is the electrical schematic that would represent what we're talking about here. So here's the coil for the bobbin that we were talking about. We have a switch, we have a battery. This part of the circuit is very, very low current. It's probably on the order of milliamps. Now the second part of the circuit, they're not physically attached. They're totally separate. Here's that lever we were talking about. Basically, it's a switch, right? So we come from the one end of the lever, which we're going to call the common, up to the normally closed contact. We're not connecting anything at the moment to that, but we could connect maybe another light bulb to it if we wanted to. Now when I energize this coil, as you saw down here, it's going to pull the lever down. So here we got that blade from the switch. It's going to get pulled down towards the normally open contact. Now the current in this part of the circuit could be very, very high. It could be on the order of amps. The current on the coil side is typically very, very low. And this is how a mechanical relay works. All right, here we have one way of drawing the schematic for a relay. It's called a single pole double throw. Now, single pole means it's got one set of contacts. That is a normally open, normally closed, and a common. The double throw means it can go either up or down in this particular case. It has two positions to move the lever that we were talking about. Now when we get to control logic, we redraw this schematic a little bit differently. And we use, for the coil, we have the two terminals for the coil, but we use a circle and we designate in the circle what the relay is. So CR stands for control relay, could be CR1, CRA, could be an M for a motor contactor. 9 times out of 10 it's CR and then CR something. This again represents the coil just like it was up here. Now the other two contacts. This is the common terminal for this relay, and then it can either go through the normally closed or it can go through the normally open. So when you walk up to it, and that means that there's no current to the coil yet, the path would be through the common, down through the normally closed, and out through this terminal to the rest of your circuit. When you energize the coil in CR1, which is a normally open contact, would actually close. The one that was closed then opens up. They flip their states. Now that's a confusing part to a lot of people, that when you look at these diagrams, they're drawn in the at-rest position. That means there's no energy applied or no current applied to the coil yet. So with no current applied to the coil, there's no continuity on this contact. That's why it's called normally open. But there is continuity on the bottom contact. That's why it's called normally closed. Thanks for watching the video. This ends the electromagnetism part. Next section up would be power. We're going to be talking about how to measure electrical power and how to calculate the power in series and parallel circuits.